Okay, here's another problem. Consider the expression 3x squared plus x minus 2. It turns out this is 0 for x equals negative 1 and x equals 2/3. If I put in negative 1, I'll get 3 times 1 plus negative 1, that's 2. Take away 2 is 0. And put in 2/3, 3 times 4/9, that's 4/3, plus 2/3 makes 6/3. Take away 2 is 0. Yes, it's 0 for both negative 1 and 2/3. But here's the question. Use that fact to actually factorize 3x squared plus x minus 2. Okay, so let's think about what we've done. We've just realized that x equals negative 1 makes this expression equal to 0. So it is a multiple of x minus 1. So actually 3x squared plus x minus 2 is a multiple of x minus 1, x plus 1. So it's x plus 1 times something with 0 error because it equals 0 at x equals 1. But at the same time, x equals 2/3 makes this equal to 0. So it's a multiple of x minus 2/3 with 0 error. So that means x minus 2/3 is also a factor. So it's the x minus 2/3 not there, so the x minus 2/3 must actually be part of this part. So I can say it's x plus 1 times x minus 2/3 times something else. All right. Because the factor theorem says if a particular x value gives you 0, then I've got that as x minus that quantity is a factor. Grand. But now look what's happening. What could that something be? This is 3x squared. And if I was to multiply this out, I've got an x times an x. And if I have any more x's in here, I'm in trouble. I'll be in the x cubes or higher. There are no x cubes. So this cannot have any x's in it. In fact, the only thing it can be is a number, no x's. So actually, maybe I'll just write a or k or, I don't know, m. I'll write m for number. M for number. All right, I'll write m. All right, so it must be 3x squared plus x minus 2 equals x plus 1, x minus 2/3 times m. Now the question is, what must the number be? Well, if you should think about it, if I were to start expanding this, I get x times m plus all the rest of it. But it's meant to be 3x squareds. The only way I'm going to get an x squared is x times m. M better be 3. So this number better be 3 by logic. So actually it factorizes 3 times x plus 1 times x minus 2/3. Beautiful. Now some people don't like fractions in this. I could actually do 3 times that one, and I could rewrite this if I wanted to as x plus 1 times 3x minus 3 times 2/3 minus 2, just squeaking in the space. So maybe that's a better factorization. I don't know, it's just a style thing at that point. Beautiful, beautiful. So again, for quadratic, we know there's going to be possibly 2 roots. So if I tell you 2 roots, that means I know 2 of the factors. What's left over can only be a number. And in fact, all the number could be, if you think about where the x squareds come from, must be the coefficient of x squared. So let me write that up as a little result, because many curricula want you to be very aware of that, and they'll test you on it. I'm not sure why, but they will. So let me write up very clearly for you, hopefully in neater handwriting. Let me clean the board. Back in a moment. Okay, so here's the general result. For quadratic, if ax squared plus bx plus c is 0 for x equals p and for x equals q, then by the factor theorem we know that x minus p has to be a factor, x minus q has to be a factor, all that left over can be a number. That number has to be the number at the front, a. Then we can say, if we've got 2 particular zeros, ax squared plus bx plus c must be a times x minus p times x minus q. That's it. That's the beautiful factor theorem taken to another level. All right, piece of jargon. If ax squared plus bx plus c, if this quadratic expression is 0 for these particular values, people will sometimes say p and q are roots of the quadratic. Just like we say square root. In fact, square root is the 0 of this quadratic, x minus 2. What value makes this 0? Well, x equals root 2 makes it 0. Also, x equals negative root 2 makes this 0. In fact, by the theorem we just have here, I've got the 2 roots of this quadratic. This must be an x minus a root 2 and an x plus a root 2, and bingo, and the number in front better be 1 because there's a 1. In fact, this is something we saw last lecture. That's actually the difference of 2 squares formula. This is x squared minus root 2 squared. X minus root 2, x plus root 2. So here, that's the reason why people call them roots again. It's the word root. So the word root, if p and q are roots of the quadratic, means if p and q give the value 0, then x minus p and x minus q are factors of the quadratic, and that basically completely factorizes the quadratic. The number up front better match the number for x squared. Got that. All right, we're getting quite theoretical, but look, we're doing the factor theorem, done. We're talking about roots, done. We've done difference formulas, we're kind of there. So the rest is just now details and practice. So let me give you some practice problems to try right now. Okay, here's another strange practice question. 1 root of ax squared plus bx plus c is double the value of the other. So 1 root's double the other. Show then that the ratio of b squared to ac must be the ratio of 9 to 2. Okay, give that strange question a try. Okay, here's quite an absurd question. If 3 is a root of 2x squared plus rx minus 3, and then if rx squared plus x plus k has 2 identical roots, then what must the value of k be? Okay, this is crazy, like, you know, lots of layers to this question. Can you work out what k has to be to make all this information hang together? Wow. Okay, let me finish off today with one final piece of algebra. But let's go back to the difference of two squares formula we had from last lecture, but actually we also now have it from this lecture, if you think about it. So x squared minus a squared, there's a quadratic. Clearly, if x equals a, I get 0. Therefore, x minus a has to be a factor of this thing. Also, if x is negative a squared minus a squared is 0. So x minus a also has to be a factor. And in fact, I've got two factors now. The coefficient in front better be 1 because I get x times x is x squared, a single x squared. Indeed, I need a single x squared. So actually, with the logic of the factor theorem, we can now deduce the difference of two squares formula as well. And we can use it in strange ways. In fact, earlier today I rushed through an example about writing x squared minus 2 as a difference of two squares, because I think of this as x squared minus root 2 squared, so it's actually x minus root 2 and x plus root 2. And since we tend to call these roots, if you like square roots and so forth, then it's kind of natural to want to call the zeros, the things that make a quadratic expression 0, roots as well. And people do, they call them the roots. So the little change of language there is a little bit perturbing, but roots just means zeros when you're talking about quadratics. All right. So this little factoid about the difference of two squares often comes up in algebra class. For example, when I was a student, we did not have calculators. We couldn't actually work out calculators. And so all we had was like tables of values, booklets that listed, the square root of 2 is about 1.414. The square root of 3 is 1 point something or other, I don't have it in my head. We went through all the square roots, went through all the cube roots, and went through all the different values you could possibly ever want to look up. So when we were doing a problem in mathematics and we had to actually work out the decimal answer to something, for example, like 1 over the square root of 2, if I was doing a problem, that's a fine mathematical answer, but if I need to know what it was as a decimal, like I was doing an engineering problem, I have to actually build something this length, then I'll need to know what it is as a decimal, then all I could do was go to my books, look up the square root of 2, and see it's about 1.414 to 3 decimal places, and then I'd have to work out, 1 divided by 1.414. This is what I would have to do as a student on my paper. Do long division, and it would be miserable. Now, on a calculator, this is fine. Just get at my calculator, go 1 divided by 1.414, and out will come an answer. But in my day, 30, 40 years ago, when I was doing this as a kid, we were taught a piece of advice. If you need the decimal, only if, you don't have to, if you need the decimal, and you've got square roots on the bottom, it can be handy to figure out a way to put the square roots on the top of the fraction instead. And one way to do that was to multiply the top by root 2 and the bottom by root 2. If I multiply the top and bottom of a fraction by the same number, it doesn't change the value, which is great, because this is now root 2 divided by root 2 times root 2 is 2. And now I can do that one because even in my head, root 2 is about 1.414 divided by 2. I basically see 14 and 14. Right now I see this is about 0.707. Much easier than doing the long division. Now in this day and age, that is easy to do on a calculator. That's just as easy to do on a calculator. It doesn't matter anymore. Though people sometimes insist, and I don't know why, I still don't know why, here we are in the 21st century, they still insist that all square roots have to be on the top line. Mathematically doesn't matter. That is a fine answer mathematically. That's a fine answer mathematically. It's just if you actually need to know the decimals, then this one's easy to work with if you happen to have a broken calculator or something. Very strange. Anyhow, so people tend to do the following things. You might be going along and you're doing some algebra problem and out comes the answer 1/3 minus the square root of 2. And you say, okay, nothing wrong with that answer. As a mathematician, fine answer. But people are still obsessed as though we don't live with calculators anymore and say, oh, I don't like that. I don't like square roots on the bottom. Please put square roots on the top. Please put square roots on the top. All right, okay. The mathematical reason is gone. This is just a strange style question. But here's the way to do it. We can actually do that difference of two squares formula. Here it is up here. Think of this as 3 minus root 2. And if I did a 3 plus root 2 to go with it, then I can see it's actually going to be a very nice expression. So let me do that. Let's put a 3 plus root 2 with it on the bottom, which means I better put a 3 plus root 2 on the top as well to keep the fraction the same. Because the difference of two squares formula tells me this should be nice. In fact, this is 3 plus root 2, and on the bottom I'll get 9 minus 3 root 2 plus 3 root 2, cancels out as I expected, minus root 2 squared. Basically 9 minus 2, 7. So this is actually 3/7 plus 1/7 square root of 2. There's the square root on the top line, there's no square roots on the bottom line. People tend to like that for funny reasons that I don't understand. Okay, that's called rationalizing the denominator. I got rid of the square roots on the bottom and put all the square roots on the top. If you wanted to, you could actually rationalize the numerator. For example, if I had, say, 1 plus root 3 divided by 5, and suppose I want to move the square roots on the bottom. I just want to for some reason. Who knows why? I could do that. I could actually do the same thing. 1 plus root 3, if I multiply by 1 minus root 3, it should be very nice. So let's do that. 1 minus root 3 on the top, another 1 minus root 3 on the bottom. That's not changing the fraction. So I'll get so x is 1 and a is root 3, so I get 1 squared minus root 3 squared. That's 1 minus 3, it's negative 2 on the top, and 1 minus root 5 on the bottom. Beautiful. I put the square roots on the bottom. The point is, you can put the square roots wherever you want. If you want them on the top, put them on the top. Want them on the bottom, put them on the bottom. It's all kind of grand. All very good indeed. So let me clean the board and we'll end off with just one practice problem for you on how to move the square roots around using this difference of two squares formula. So back in a moment. All right, the final problem for today. Please write 60 minus the square root of 2 or divided by 1 plus the square root of 2 in the form a plus b root 2 where a and b happen to be whole numbers. Can you do it?